So, hello everyone. I'm gonna take a start on this because we are already 1 minute late and we have to use the time very efficient. My name is Hulya. I will be moderating the first session, which is about long span bridges. And I will give 25 minutes to all the presenters. But this 25 minutes will include the short introduction of the speaker, the presenter themselves, and also include the replying the questions. And if there's no time left after the presentation, the questions can be replied via online through the chat option. So I will now get Dardan as a first presenter to talk about the seismic analysis of an irregular bridge. Hi, Dardan, you are here?
Hello, yes.
Okay, make the good use of your 25 minutes and please start.
Okay.
Thanks. Bye.
Thank you very much. Good morning to everyone who is attending the conference and listening to this presentation. First, I'd like to introduce to all of you myself. My name is Dardan Perdibuka. I'm a structural design engineer working for Edge Consulting Engineers. I got over 4 years of experience in the field of bridge design and analysis, and I also am a PhD candidate at the Kandilli Observatory Department of Earthquake Engineering. Before I begin with my presentation, I really would like to spare a minute to express my deep sense of thankfulness, which I strongly believe is shared by each and every one attending this conference, to express the thankfulness to the wonderful people who, in my point of view, have put a great deal of effort in organizing this conference, specifically through this, as we are passing through these difficult times which have indeed restricted our social beings and social lives. Also, special thanks are for the sponsors of the conference, most notably being the General Directorate of Highways of Turkey, which I believe have not refrained their material and moral support to the conference. So once again, thank you very much to all who has been involved in this organization, and it is the very sincere desire and hope of mine and my colleagues that this study and presentation of ours will be of any benefit and would add any value at all to this conference. So if we come to the presentation, our study has to do with the comparative seismic analysis of a 6-span long irregular bridge, a bridge which is classified as irregular as per the requirements of AASHTO LRFT bridge design specifications. And the comparative nature of our study is based on the fact that the analysis was completed by utilizing 2 different methods, and then the results were compared. The outline of our presentation includes the following parts. In the initial part, the basic concepts, I will be summarizing some of the basic definitions about bridges. In the principles of seismic design of bridges, well, obviously, I'll try and summarize some main points and philosophies regarding the design of bridges to withstand seismic forces. The analysis methods part obviously contains the methods which are most widely utilized in practice to analyze bridges. Study layout contains information about the aim of our study and the structure of our study. In the analysis results, the results obtained at the end of our analysis are summarized, and eventually in the conclusions part, summarized are the most important outcomes of our study. To start with the basic concepts, in particular with the definition of a bridge, one might be able to define a bridge as a structure which provides us safe passage over either man-made or natural obstacles such as valleys, bodies of water, and other rough terrain by means of spanning these obstacles through natural or man-made materials. Indeed, bridges are very important structures which have been around for a very long time indeed, and the historical development of bridges, it is safe to say that historical development follows the historical development of humankind itself, and that the materials, the methods which are utilized to construct bridges have evolved as has evolved the technology and the science of materials. Among the first forms of bridges, or the most ancient forms of bridges, are the so-called clapper bridges or natural bridges, which basically consist of flat slabs of stones, chunks of granite, or trunks of tree flown in a river, for instance, and such. When we come to the first examples of man-made bridges, we have the stone arch bridges, and it is widely believed that the oldest stone arch bridge, which is still actively being used, is actually a bridge in Turkey. It is called Caravan Bridge and is located in Izmir over a river Meles. Another fascinating example of stone arch bridges is the oldest bridge in China, the Great Stone Bridge, or Anji Bridge, I think it is called. It still stands still after being constructed over 1,400 years ago. As time progresses, iron becomes a prominent material in the construction of bridges. Particular examples include the Coal-Brookdale Bridge and Britannia Tubular Bridge, which are constructed using cast iron and wrought iron sections. These are followed by examples of truss bridges, which utilize steel as a construction material. And then we come to the 19th and 20th century, we see that newer technologies have begun to be utilized widely in the construction of bridges.
Dardan?
Yes.
Sorry for interruption, but you should move to your real presentation, please, because you only have 10 minutes, not even 10 minutes left. Please.
Okay. Okay.
Yep. Very quick.
Okay. So these are the main members of a bridge.
Skip this, please. Everyone knows about it.
Yeah. Okay. Yep. Principles of seismic design. I think it would be reasonable to say a couple of words just for understanding. So if you are about to design a bridge to withstand seismic forces, the roadmap which we should follow is a little bit different than the roadmap followed, for instance, the design of a bridge under dead loads. The difference is that if you design a bridge to withstand dead loads, the main aim is to ensure that all structural members of a bridge will remain basically elastic during the action of this force. However, when it comes to the seismic design of bridges, it is not possible to make such an assumption because it would not be economically feasible. Therefore, modern seismic design approaches assume that a bridge will inevitably undergo some sort of damage or inelastic deformation when it will be subjected to a very large earthquake. So plastic hinges are loads only in the piers of the bridges, and those are in earthquake engineering energy dissipation mechanisms which allow ductile behavior of an otherwise rigid element of a bridge, piers in this case. So there are three steps in seismic design: performance level determination, demand analysis, and to perform a capacity design. Capacity design is an approach which aims to develop a complete load path in the bridge and a structural configuration that would ensure that initially the ductile members of the bridge will yield, and afterwards the other elements of the bridge will remain intact, or in other words, will remain within elastic limits during an earthquake. It is best described through the chain analogy, the well-known chain analogy of Pauli and Priestley. In this analogy, basically the chain represents the load path of a bridge. The tensile forces acting on both ends of the chain are the earthquake excitation in the real world, and the links of the chain are basically the elements of a bridge. So in this analogy, this chain has one ductile link, whereas the other links are brittle. So in case where the strength of the ductile link is less than the strength of the brittle links, when a large force is applied onto the chain, initially this ductile link will fail, and this will force the entire system to fail in a ductile manner. Whereas if the force of the capacity of the brittle links would be less than that of the ductile link, then the entire system would fail in a brittle, sudden, and a rather undesired way of in such a way. And this basically underlines the importance of the capacity protection of the other elements in addition to the yielding elements of a bridge. So this is the load path. I'm going to pass this one. Regarding the analysis methods, they are divided basically into elastic methods of analysis and nonlinear or inelastic methods of analysis. Among the methods listed here, we have used in our study the multimode spectral method and the fast nonlinear analysis procedure. To shortly say a couple of words about these methods, the multimode method basically is based on all of the modes that have an important contribution to the overall response of the bridge. And the most important thing about this type of analysis is to ensure that sufficient number of modes are included in the analysis, and this is achieved by means of checking that the summation of the modal masses is at least equal or larger than the 90% of the total mass of the bridge. The second method that we have utilized is the fast nonlinear analysis procedure. It is otherwise known as Wilson's procedure. In this method, what we basically do is that in our structural or mathematical model of our bridge, we only model the members which are supposed to behave in a ductile manner during an earthquake as nonlinear elements, whereas the rest are modeled as linear elements. By doing so, the final form given here of the equation of motion of a bridge basically yields an equation where there are only two terms which need to be updated after each time step during the analysis, and those are the stiffness matrix of the nonlinear elements and the vector force which is associated with the nonlinear elements. These vector forces are represented in most of the softwares using nonlinear link elements, and also in our study. So if we come to our study, the aim of our study was to perform a dynamic analysis of a 6-span 180 meters long irregular bridge by using the multimode spectral and fast nonlinear methods of analysis. The aim was to compare the results and investigate the effectiveness of the methods and find out the differences. Also investigate the outcomes of neglecting the effects of structural nonlinearities on the analysis results. And finally, to make an assessment whether making a trade-off among the analysis time and accuracy is actually tenable or a reasonable action for a bridge, for an irregular bridge such as the one we have considered. This is a description of the bridge that we have used. As I said, it's a 6-span long, 180 meters total length of the bridge, with each span having a length of 30 meters. The cross-sectional width is 12 meters, and it's not a curved bridge. Skew angle is 90 degrees. It has I girders, pre-stressed girders, and the substructure is made of a single circular column having a diameter of 2.5 meters. One interesting point about the structural layout that we have chosen is that as per the guidelines given in the Ashtoyler FT Bridge Design Specification, chapter number 4, our bridge basically fits into the boundary of regular and irregular bridges, in a sense that if we take a closer look at this three first requirements, our bridge is a regular bridge, whereas when we investigate the band pier stiffness variation from one span to another, this value is slightly larger than 2. So we thought that this bridge is basically at the boundary of regular and irregular definition. It is an important consideration because there is another table in AASHTO in the same chapter which guides us as to what should be the method of analysis with regard to the seismic zone and type of bridge. Our seismic zone is 3 in our study. Our bridge was considered to be a critical bridge. If it were a regular bridge, which could be considered with regard to the requirements given above, it should be analyzed. It is advised that it should be analyzed using the multimode method. However, if we consider it to be an irregular bridge, then the time history method is advised to be used in the analysis. So basically, we used both of the methods to see what kind of difference we would find. This is our analysis model, the mathematical model of our bridge. So the superstructure or the deck of the bridge is modeled using shell elements. All other elements, pier caps, piers, and girders are modeled using frame or stick elements. The connection between the superstructure and the substructure was achieved by means of linked elements, which are available in the software. Except pier caps, all other elements of the bridge are modeled using modeled as linear elements, meaning that their stiffness would not change during the course of analysis. However, piers were modeled as nonlinear elements, and as the only source of nonlinearity in this study, to represent the nonlinearity of the bridge, we needed to perform a moment curvature analysis, and I'm afraid due to the time limitation, I won't be able to go into the theoretical details of it. But basically, we found the plastic moment capacity of our piers, entered it into the software, and later we needed to define the plastic hinge models in our structural model, and this is achieved by means of multilinear plastic links available in the model. Shortly, the reason why we have done such kind of an action was to actually represent this hysteretic behavior of our columns during an earthquake, which is nothing more than just the changing of the or variation of the stiffness during the application of the earthquake excitation. About the input ground motion, for the multimode response spectrum, we have used a 5% damped acceleration response spectrum belonging to a particular design earthquake, which has a return period of 975 years. On the left-hand side, given is the actual response spectrum, acceleration response spectrum used in analysis. Whereas for the fast nonlinear analysis, time history analysis, we have adopted 3 sets or pairs of ground motion. By pair, I mean a ground motion which has 3 components, 2 horizontal and 1 vertical. However, the raw form of this ground motions could not be used in the analysis since they needed initially to be scaled such that their corresponding response spectrum would match that of the design earthquake. So shown here are the scaled and final versions of the input ground motions used in the analysis. Analysis results were obtained in terms of pier head displacement, maximum pier member forces, and deck displacements. I will be summarizing the analysis results in the conclusion part, but shortly, as you can see in these plots, for all considered response quantities, it was found out that the time history analysis resulted in higher results when compared to the response spectrum or multimode analysis method. So if we come to the conclusions,
you have 7 more minutes, Dardan. Sorry, 7 more minutes. Yeah, you can make your conclusion in a relaxed manner. Yes. Okay. We reached the conclusion at the end of the analysis that displacements occurring at piers obtained via time history analysis tend to be greater at all piers when compared to the results obtained from multimode response spectrum, and the highest displacement value was attained at pier number 3, which happens to be the tallest pier. In terms of maximum pier force effects or member forces, which were obtained in terms of bending moments and shear forces, the results tell us that the values obtained through, again, time history analysis are larger than the values obtained through multimode response spectrum, and the difference in bending moment values were as much as 28% for the longitudinal direction, whereas for shear forces acting on the piers, this difference reached up to 50% in the transverse direction of the bridge. And lastly, the last response quantity we checked was the deck displacement in longitudinal and transverse directions, which were observed to be higher for the case analyzed using time history method, in particular the Northridge input case, which was also plotted in the previous plots. And a difference of as high as 32% was obtained in the longitudinal direction values. And the final word is that the concluding remarks given above are a clear indication that when we are about to neglect the effects of nonlinearities present in the structure, this could significantly alter the analysis results and may even lead to unprecedented and fatal errors, especially when a bridge structure gets longer, has tall piers, and is classified as an irregular bridge. Being so, the geometric, material, and geographic properties should all be carefully considered before the construction of the bridge mathematical model, and there should be a high level of alertness while making the trade-off among the analysis time and the accuracy of the yielding results. This was basically all I had to tell. I thank you very much for the patience and listening to me. If there are any questions, I would love to answer them. Thank you. Thank you, Dardan. Are there any questions for Dardan? Because we have 4 more minutes. He used the time very efficiently later. So, any questions? So, Dardan, maybe you may give some words on the, in here you have 30% difference and 50% difference between the analysis. So what would be your conclusion? Which method should be used, for example?
Well, for this type of a bridge, for this structural layout that we have considered, the time history methods actually would be the correct choice for the analysis of the bridge, we believe. I mean, of course, the multimode method would reduce the time of execution. However, as we see from the results of the analysis, there is a huge difference between these two methods. Therefore, for this type of bridge, which can be considered either regular or irregular, it is advised that one should use the time history method to analyze the bridge.
Okay, thank you very much for your presentation.
Thank
it
you.
was very useful. Yeah.
Thank
So
you.
we can move on to the next presenter. So I think it's Jesper. Hi, Jesper.
Hello, can you hear me?
Yes, we can. Yeah.
That's good. Perfect. All right, should I just start?
You have 2 more minutes to start talking, so we can say welcome.
Yeah.
Unfortunately, you are not in Istanbul.
No.
And
no.
yeah,
All right.
maybe you have to wait 2 more years for that.
Yeah, exactly. Yeah. I will start then. I just also would like to say thank you for giving me the opportunity to participate in this conference and present the Hålogaland Bridge. I would have loved to travel to Istanbul, but during these circumstances, it must be next time. I will share my PowerPoint.
Yep.
You see it?
Yep.
Great. All right. I'll start. My name is Jesper Pihl, and I work for the major bridge department in Kobe in Denmark. I'm specialized in suspension bridges and in particular cable structures. I've been so fortunate to be able to work on both the Osman Gazi Bridge in İstanbul Bay in Turkey, and actually now I'm working on the 1915 Çanakkale Bridge. But today I will give a presentation on the Hålogaland Bridge in Norway. Just to put where we are, if you look at the upper right corner, you can see that we are in very northern part of Norway. Actually, we are 300 kilometers north of the Arctic Circle, and this Hålogaland Bridge was built to shortcut the road which goes into the fjord. If you look at the lower right picture, you can see the red road and the fjord. And what was done from the city of Narvik was that first there was made a road leading into a tunnel on the one side, a 300-meter long tunnel, and just after the tunnel we have the bridge itself. So my agenda today will be first the design philosophy of the cable structures, and in particular what we've done differently from what you could say what we've done differently in this project. And then my second part will be the construction of the bridge. So to get started, the Hålogaland Bridge is a suspension bridge with a main span of 1145 meters. It has A-frame pylons, which is a pylon, the 2 legs will meet at the top, and that will cause, if you have 2 cable planes, that you will have spatial cable planes, 3-dimensional cable planes. This is a feature, it's aesthetic, but it's also due to aerodynamic stability. The one other thing to mention is that we're having a very narrow deck. We're only having 2 lanes crossing. So we're having a 18.6 meter wide deck spanning these 1145 meters. So this makes it a challenge when it comes to aerodynamics. Just to take a brief look at the overall layout and the bridge articulation of this bridge, as you can see, it's 1145 meter main span, and it has no hangers in the side span. It has backstays. And just to go through the philosophy of how this was chosen. As you see, we have the 1145 meters, and we are choosing our footprint very wisely. Actually, there was a project which has positioned the two towers onshore, making a longer span. But we found that at this specific location in Norway, we actually were able to go offshore because we're having a small plateau where we can put the towers in the fjords. It should be mentioned that in Norway, they're having very, very deep fjords, and most often the towers will be on land. So we're choosing the 1145 meters as the minimum main span due to economic reasons. Then we're choosing the two T-points, the theoretical points at the tower tops, and they are chosen to have a stack to span ratio of 1/9. As you can see, there is, as we talked about the tunnel at the one side, we try to minimize the tunnel excavation. That was done by moving the towers offshore into the water. We were able to have a longer viaduct span at the if you say the left end. So we were able to bend the bridge earlier and minimize the excavation of tunnel dramatically. But also, as you can see, that we're having different T-point heights, so it's not symmetric. And actually, the entire bridge was tilted, so that we also had a higher, point at the left side at the Narvik city. So we were able to minimize the excavation as well. Furthermore, we chose two anchorage points where we had some good rock, and they are not symmetric either. So to speak, here we are playing with non-symmetry. If you would have a normal suspension bridge on a flat sand bottom, a symmetry would be natural, but it's not needed. So this is one of the things. And then, of course, if you look at the lower the picture, you can see that the main cable has a distance of 3 meters at the towers, but 15.6 meters at the midspan. This is due to the spatial cable plane. Actually, when we come to the construction, you will see that the main cables will be parallel with 3 meters during the entire construction process and be pushed apart later after the making of the main cables. To talk about the overall layout and bridge articulation, this is a relatively small suspension bridge, and it's light because the deck is not that heavy. That makes the cables small, and as you know, the stiffness on a suspension bridge comes from the main cable. It's geometrical stiffness. I've shown here a video of a bus passing the Beaver Bridge in Arkansas. This is a bridge with a 10-ton capacity, and this is a 30-ton bus. And I'm not sure how well the video is, but as you can see, you have very large deformations. And this is actually what we see in these relatively small suspension bridges, that we have huge impact on traffic load. It's a very lively bridge. And this makes the bridge articulation important. And if you look at the right side, you can see on the middle, you can see that we've chosen to use the bearing as pendulum bearing, which is a bearing that will be able to take both uplift and compression. It stabilizes the deck from rotation. Then we're introducing a wind bearing, which restrains the transverse forces. And then we are using buffers at the bridge ends to control the displacements at these expansion joints. Design of cable structures. If you look here, you can see that we will start out with the main cable, and then we're having the two tower saddles. Going down the main cable, you will see the cable clamps and the hangers. And then, of course, the deck will be suspended in the hangers. And then in the end, you will see that we're having the anchorages as rock anchorages. That's a huge advantage in Norway, that they have a lot of rock. So the way that you will do the splay chamber as anchor chamber is by just drilling some holes in this rock. It's a very efficient way, instead of, as we normally do, having this gravitation anchor block, which will hold back the main cable force from weight. So here we're having the anchor, the rock anchorages. But so to speak, I will present the design of the main cables, the saddles, the cable clamps, hangers, and the anchorages. This is the cable structure components. But first of all, before we can do any design, we need a FE model, and the global FE model is the backbone of modern suspension bridge design. As was mentioned earlier, we're taking the analysis to a new standard by having these FE models. It's a geometrical model, and it will be transformed into finite elements. We're using an in-house program called IPDIS, but other programs can also be used. The analysis that we undertake during a design of a suspension bridge is, of course, static analysis. This is the influence surface of some traffic. Then we are looking into the dynamic wind analysis. As you saw for the traffic load, the bridge is very lively, very flexible. The same goes for the wind. So we need to do the dynamic wind analysis. It's done by taking the wind spectrum. It's a spectral analysis where we take the spectrum and multiply onto the frequencies of the bridge. Then we are looking a lot into hangar rupture. It's a severe case for suspension bridge. So we are doing time history analysis of the hangar ruptures with a sudden loss of a hangar. Then actually we're spending a lot of time on the hangar rotations because as you know, hangars are very good at taking axial forces, but they don't like bending. So to be able to have a safe design and a durable design, we are introducing spherical bearings and cylindrical bushings at the shortest hangars. But to be able to know where they are, we're doing some analysis on that. And then finally, I would like to highlight that one of the advantages with the FE program is that we can do semi-local analysis. It means that we can actually activate part of the global FE model and have it as a shell model or a solid model. So here for the Hålogaland bridge, we had some complicated geometry at the lower part of the legs. So actually, we did one of the legs or one of the towers as a shell model in the global FE model and looked onto the stresses in more detail. All right, design of the different components. These are design of the main cables. And for the main cable design, I would like to mention John Roebling in the lower left corner or right corner. He was a German immigrant to America, and he's most known to be the chief engineer for the iconic Brooklyn Bridge. But before that, he was actually dragging canal boats on shore, and they used some hemp rope, some natural rope, and it broke all the time. So he was annoyed by that, and he decided to develop what we now know as high-strength steel wire ropes. So he did that, and he's actually one of the reasons that we're having these very, very high-strength wires of approximately 2,000 megascale. So the main cable is normally built up from these 5 to 6 millimeter small wires. They are made into a strand of 127 wires, and then this strand is built up until you get the main cable. And on the upper left, you see a standard main cable, hexagonal shape, a bit higher than wider. It will then be wrapped by wrapping wire, and then finally elastomeric wrapping to secure the durability by dehumidifying the cable. But for the Hålogaland bridge, we chose to make a square main cable. As you see in the lower part of the picture, you can see that we're having a square main cable, another hexagonal main cable, and then gave a lot of good things at the saddles and at the anchorages, but I will come back to that later. Of course, it was compacted into a circular shape, as you see in the upper right corner, and then yeah, that was the main cable. Just to go briefly to the design of the saddles, the special thing for the Hålogaland bridge was that they are designed only from welded structures. So it's plated steel welded together only. We are not using cast steel for the troughs, as usual. And this makes very good sense when you have the square main cable shape. As you look at the left splay saddle, you can see that you have a square trough, and it fits very well with the square shape of the main cable. We're looking into stresses and stability, and when we're doing this, these are S460 high-strength steel. So when we're doing this design, we look into the strain because we will accept a bit of yielding at the ULS. Otherwise, the design will be way too robust. The cable clamp, the design of the cable clamp is also a little bit special. It's also a welded structure. Actually, the contractor was given the choice whether he wanted a cast steel or welded steel clamp. It's a rather small clamp due to the small main cable force and the small main cable area. It's made with a philosophy of dehumidification. So it's made in a way so that the bolts, the tie bolts or the tie rods is, so to speak, put outside the clamp structure, and you're able to seal the gap between the two clamp parts behind the bolts. If you look at the analysis, it's a 3D analysis. It's made in the program Abacus, and it's made with contact surfaces to be able to assess the right membrane forces in the clamp when tensioned. Of course, also in the bottom picture, you can see that we're looking into the pin and pinhole connection stresses. Design of hangers. For the Hålogaland bridge, we're using the full lock coil cable, which has been used widely in Norway and in Europe. You can use a parallel wire strand as well, but we're using the full lock coil cable, and on top of that, we're actually extruding it by the HDPE sheathing, 7mm thick sheathing. As I briefly told you before, we are taking very good care of the bending in our cables or in our hangers. So we're introducing bushings at the cable clamp, and then we're using a spherical bearing, which will allow the hanger to rotate at the anchorage to the deck. Of course, on the right, you can see that we're having the socket, which is cast steel, and which also undergoes FE analysis. The design of anchorages are interesting because for a normal bridge, you would design with a curved surface, as you see in the middle top, where you are curving the surface where you are putting your anchorages. But if the video plays, you can see here that we're going into the anchor chamber, and from the splay chamber to the anchor chamber, all the post-tensioning cables are actually a square main cable allows us to have a very compact layout at the bottom of the splay chamber, as you see in the bottom middle. Again, we're doing a FE analysis to secure this anchor plate, the crosshead slab of this structure. The design of bridge to deck, I will not go too much into it. It's a closed box. It's a thin plate, autotropic. It has a plated diaphragm, 12mm. It's only 18.6 meter wide. And one of the interesting things was that the aerodynamics of that bridge deck was very important. I don't know if you can see this, but they was doing a terrain model of the landscape in that fjord in a wind tunnel to get the right turbulence. And then in the middle, you can see that a lot of section models, also including cars, were done to give the aerodynamic parameters and also the critical wind speed. So to the construction of the bridge, when you're doing the suspension bridge, you will fabricate, especially for the steel or for the superstructure, you will fabricate all the components elsewhere. You will bring them to site, and then you will actually install them. And I will go into the fabrication of the component and then the construction. And you can lift the segments directly from the vessel. But first of all, the deck fabrication. As you can see in the lower left picture, they were done in China, and they have some very, very large facilities. A very large portion of the deck is being put up onto this scaffolding. The deck is fabricated with a camber, which can be taken into account by this scaffolding. You can see on the upper left that we have a lot of automatic welding of the troughs. Then when you have a final deck, it will be painted and surface treated and ready to be shipped. Same goes with the saddle fabrication. These are also welded. They are rather thick plates, between 120 and 50 millimeters, welded together and painted and ready to be shipped. For the main cable fabrication, the main cable for the Hålogaland bridge is a prefabricated parallel wire strand. It's not the air spinning, as can be done as well. This is prefabricated, which is probably the thing you would do mostly today. You are simply just forming the main cable, and you can see here how they've made the socket in a mold, and you add the socket, and then your main cable will be ready to go. It's a different thing for the hanger fabrication. These are actually made from a spun cable. So you will form the cable, but when you form it, you will spin the cable in different direction to make this spun cable. It's a lock coil cable, so the outer layers of wires will be set shape and will be locking. If you look at the video on the right, you can see how they are actually taking that final lock coil cable and extruding the HDPE to make it more durable and long-lasting during the lifetime of the bridge. Then the cable clamp fabrication should be done. This is, as we said before, a fully welded clamp from plated steel. So you're having the rather thin 20mm membrane, and you weld the tooth area on both sides, and of course the eye plate. Then very briefly onto the tower erection, whereas the steel structures are made outside the site and then transported, all the concrete is made on site. So here we are doing the caissons for the two tower legs. And here we see that we are doing the approach bridges and making the tower. Construction of anchorages, as said before, it's rather easy to anchor suspension bridges if you have rocks. They drill a hole, and then on the lower left you can see that this is the anchor chamber. So they take the post-tensioning cables, and then they make the anchor plates ready. The anchor bolts are installed, and then they're ready to install all the main cable strands. Installation of tower saddles, because they've already made the viaduct bridge, as you see on the upper left corner, they're able to transport the tower saddles all the way to the tower, and they're simply hoisted up from the hauling system also used for the main cable on top of the blue steel structure, and the tower saddles were lifted and then put in place. Installation of the catwalk. This is one of the very, very large temporary structures to be made. This is a catwalk which is only used to do the main cable installation. It was done here in very nice weather. So yeah, that was done firstly. And then when you've done the catwalk, you were able to haul all the main cable from one side to the other. It was done, as I said, with the PWS. So here we have a strand which is being hauled over the two tower saddles and being mounted on the other side. So, and at the lower bottom, I just want to show some pictures on how it is to do main cable installation during winter time, 300 kilometers north of the Arctic Circle. These are very, very harsh conditions. So it was very cold and very windy, but we managed to do it. Finally, the pre-compaction and the hydraulic compaction of the main cable. It was a bit interesting to see how it would be compacted. Now we didn't have this hexagonal shape, but it all went well, and it was compacted into a circular shape. So this was good. And then the transfer shifting of the main cable. On this left-hand side video, you can see that some blue steel struts were installed, 7, and a device which were able to push the two main cables apart was used. And actually, one interesting thing was that the catwalk was made as one catwalk, and it was split together with the main cable transfer shifting. On the right, and I will finish in 3 more minutes then.
Yeah.
Finally, the installation of the cable clamps. As you can see, this is the clamp on the right. The stainless steel bolts are outside the sealed area. And the round steel wire and elastomeric wrapping, the main cable should be wrapped by steel wire, and at the end it should be wrapped by the elastomeric wrapping to secure the dehumidification. Then we are installing the bolt and use a very big hammer to install it. The tolerance is very tight due to durability, but they made it very well here. Then finally, period of time which were done to install the entire deck. And my final thing is that actually when this deck was installed, there was a lot of ongoing works with the welding of the boxes. It was a very cold period, so it gave a little bit of problems, but in the end, the skin plates and the troughs are welded together. So that was actually my presentation, and I have just brought some pictures of Northern Lights. And I think if you have the possibility to go to the northern part of Norway to see Northern Lights, you should visit the bridge. Actually, all suspension bridges in Norway are accessible by foot, so you can walk on them, and you can see a lot of the structures. So I think it's the end of my presentation. Thank you.
Thank you very much. And we should remember to get our jackets before we go there.
Yeah.
So are there any questions? I don't know, but I would like to ask you a question because we have 1 more minute. You mentioned using the spherical bearings under the shortest hangers.
Yes, that's correct.
I understand it right? Yeah. How did you use them? Did you use them for the connection or? Yeah,
I use it. The connection between the socket and the deck anchorage plate.
Yep.
We will use them to be able to limit or minimize the bending stresses in the main cable or in the hangers, of course.
Or in the hangers, yeah.
In the hangers, and they were only used for the shortest hangers, which gets the biggest rotation. The hanger can have approximately 3 degrees of deflection before the bending stresses gets too high.
Okay.
So for hangers above that value, we are introducing these spherical bearings to take care of them, so to speak.
Okay. Yeah, that's very useful. That was very interesting, and thank you very much.
Hulya, there's a written question. I wonder if Jesper would care to answer them so that we benefit as well.
Yeah, the first one doesn't, it's not his bridge, but the second one, you can read the question. Jesper, if you can see it. Jesper,
yes.
So, yeah.
The first one with the A-shaped pylon, that's not the case. They don't resist a lot from horizontal load. I mean, the hangers are the hangers are only 3 degrees inclined, so it doesn't give any effect on the horizontal loads. And then the other one, so the elastomeric wrapping is actually to be able to protect the main cable from corrosion. We're doing it also with the Osman Ghazi and the Irregular bridge. It's very difficult to replace the main cable. So the main cable should last for the 100-year lifetime, 120-year lifetime of the bridge. And therefore, we are now actually forcing dry air into the main cables to make them below 40% of relative humidity. For the older bridges, they were wrapped in a zinc paste and they were painted. And they did as good as they could, but actually we see in America some bridges which have issues with the main cables and corrosion.
All right.
And that is actually, it's cheaper to do a new bridge than replace the main cables.
Okay, thank you very much.
Yeah.
Jesper. So now we have to move on to Selcuk, to the next presenter, and he will be talking about another famous bridge of today is Yavuz Selim. So hi Selcuk, you here?
Hello.
Selcuk?
Hi.
Hi.
I'm here.
Yeah.
I hope everybody can hear me and see me.
So I cannot see you, I can hear you, because maybe Jesper, you should just stop sharing your screen, I guess. Yeah. Thank you.
Now it's okay. Hi. Should I open my presentation from this side or you will provide it?
I think, yeah, you can share your screen if you have your presentation ready. Yes.
Okay, just a second. First, thanks for all participation and inviting me this special event. I'm the president of the Heavy Transporters Association in Turkey. So let me open my presentation. I hope you can see everybody, right?
I can see it, yeah.
Okay, perfect.
So does everybody, I guess.
Okay, yeah, nice. I want to share with you some topics, 5 topics related with the heavy transportation in Turkey, which 2 of them, one of them directly related with the Yavuz Sultan Selim Bridge, which is the last one, third one. and also indirectly with Yavuz Sultan Selim Bridge because of the restriction to use the highway by heavy transporters, heavy haulage companies. So let's move to the first topic. The Yavuz Sultan Selim Bridge opened to traffic in August 2016, especially for truck and bus traffics. But unfortunately, heavy transporters in Turkey not allowed yet to pass through the Yavuz Sultan Selim Bridge, neither by second and first bridge. We forced to use the Boro services from Dardan state and Bosphorus states, both of them. Second topic is width of the tolls connecting the Yavuz Sultan Selim Bridge to the highway traffic, 4.5 meters, which allowed to use by overweight passage of 4.35 meters. In fact, 6.90 meters allowed for overweight passage in Turkish highway and road system. At least one toll, which we kindly suggest, and our humble opinion, necessary to open in Fenertepe and Mecidiye locations. Should be open till overweight passage of up to 6.19 meters. All of you knows the technical specs of the Yavuz Sultan Selim Bridge. I will not tell one by one, but important point for us, 4 by 4 lanes for vehicles available, and even that will be 1 by 1, 1+1 railway system in the future, as per information provided us by the operation company, management company, ICC İştaş. Also, that part is very well known by all participants. I won't want to repeat again. Yavuz Sultan Selim Bridge is one of the biggest bridge due to 329 meters of height and 59 meters of width. When established next phase, Yavuz Sultan Selim Bridge able to accept 2 sets of the rail car passage same time. Weight restriction, unfortunately, still 54 tons, which is, as per legislation, ruled on 1973. I'm repeating, 1973, when the first bridge opened to car traffic. Weight limits of the Yavuz Sultan Selim Bridge much more as per available info provided by IC İştaş management company, but also they say we cannot decide what should be the maximum weight limits. You have to talk with the highway authorities as a main owner of the bridge. Therefore, as transportation company, we need to use the Yavuz Sultan Selim Bridge, means deeply request to increase weight limit to 150 tons in minimum basis. Even we are confident up to 600 tons is possible according to technical specs of the Yavuz Sultan Selim Bridge. That's not related directly with the Yavuz Sultan Selim Bridge, but also indirectly related. Speed limit for heavy transportation is 50 kilometers per hour. Thus takes 7 days if we drive from west and east borders of the Turkey. Therefore, we deeply request to increase speed limit up to 80 kilometers. Okay, if safety is concerned, let's make 70 kilometers per hour, which will be benefit of short transit time to speed up deliveries. Short transit time also to be benefit of the traffic congestion, definitely. Also positively affect logically to be valid for pollution and carbon footprint to be less. Just for comparison, I'm sure you see in the down of the recent slide, speed limit in Germany 80 kilometers per hour, Holland 80 kilometers per hour, and Turkey unfortunately 50 kilometers per hour. Permission of highway drive, less traffic congestion in city centers, centers and standard road network. Right now, highway drive is not allowed by the authorities for heavy transportation. That's why we use the state roads, which also pass through the villages, cities, and the towns. So if we use the highway, traffic congestion and the risk of the accidents to be less. Therefore, we deeply suggest to allow highway use for heavy transportation. The point is, authorities is little bit has a concern that the heavy transportation will damage the highways. But according to rules in Turkey, there is maximum weight limits per axle. So whether you have a truck, standard truck, tilt trailer, or lorries, or truck, or heavy transportation, special trailers and truck, you are allowed up to specific weight limits per axle. So in Germany, highway network preferably used. Holland also same, but Turkey not allowed. Night drive, that's another concern. As an association, we are in touch with the authorities last 6 years and last 4 years deeply to get it, but unfortunately we can't get it too. Truck trailer and escort car lighting much more effective during night drive when compared with daytime. Thus positively affects safety of truck. The authorities has a concern, worries that the truck and the escort car lightings will be not sufficient during nighttime. But we provided the highway authorities draft of the special regulation for heavy transportation, and we already give them some pattern of the traffic lighting of the escort cars. Very strong, powerful lights, like all these lights. Summer heat in Turkey negatively affects surface of the road and asphalt, melting some weeks at some roads, of course, not all of them, during summertime. So if we pass through roads during the nighttime, it will also positively affect such damage condition, which condition also possible to damage during the daytime by the trucks, trailers, not valid for heavy trucks. Night drive also positively affect lifetime of the tires and the cooling of engine to be better. In Germany, night drive allowed. In Holland, same, but Turkey not allowed at all. That's it. Thanks for listening me. It's short presentation in order to avoid to bother you too much. Alo?
Hulya, sesin kapalı.
Hulya.
I have to repeat myself. Thank you very much. I think it was very useful information. And yeah, you may reply some of the questions. And first is mine,
Sure.
because you mentioned about the night drive. Could you go back to that presentation? That's right.
Sure.
Yeah, that one. Yeah, is that only for the highways or?
No.
I believe so.
Valid for all kind of the traffic roads around of Turkey.
Yeah.
Even we are not allowed to pass through roads in city limits, which we need to get the special permission from the municipalities. In order to get it. And it's, I mean, it's really a little bit ridiculous, I can say, because all roads, standard roads in Turkey, pass through villages, towns, and cities. If we are not allowed to pass through city limits, then we have to use the highways. logically,
Yep.
but it's not allowed to. I mean, it's a little bit, I don't know how to say it, but dilemma. I mean,
Not reasonable, maybe?
Yeah, I mean, conflicts with each other. So, I mean, if we are confident that we are one of the country in Europe, so better to follow the legislation in EU. So if the Germany and Holland use the same system for their roads, so we should follow it. I mean, logically, I'm sure the technicians and the engineers in Germany and Holland make special tests whether night drive and highway use better or not.
Okay, yep. Are there any questions to Selcuk regarding his presentation? Maybe you should go to your first slide and you might, yeah, could you please? Yeah, the first one, yeah.
Indeed, there are a lot of things challenging us, but they are the main topics, I can say.
Yeah, I think it's like your conclusion as well, your first presentation,
Exactly.
because you suggested to increase the speed limit here, and the 50 kilometers is indeed a very low speed limit.
Exactly.
Yeah.
I mean, 50 kilometers speed indeed open to accidents, because the convoy length of the heavy transportation is becoming 150 meters, including escort drivers from the aft. Maybe 180 meters. So if your speed is 50 kilometers per hour, logically the other car drivers won't be the patient, and they will try to pass through in left lane of your truck. But if you are over it, then escort drivers will be in trouble to stop them or slow down them to get the safety of the road and of course cargo shipment carrier as a heavy transportation.
Yeah, certainly. These are very interesting information. So when we see a truck in front of us at night time, we can ask for their permission, as I understand.
I mean, right now, the daytime transportation allowed, and if we need any nighttime transportation, we need to get the special permission. Of course, it's bureaucracy, you know. I mean, and sometimes local authorities cannot understand what means of the heavy transportation and why we need the nighttime drive. Let's say just one basic sample to you. Heavy transportation is one of the heavy transportation is wind turbine projects. So the blades, which is very long, I mean 72 meters or 84 meters of the blades, we need to transport from the factory in Menemen or Bergama to Izmir port in order to export. So we need to export something to make positive effect to our economy, right? So you know the Izmir port is in the central city. So if you arrive to the gate of the port at 8 o'clock, you will be totally in traffic jam. So what you need to depart from the Menemen or Bergama at 3 o'clock or 4 o'clock a.m. in order to be in port gate at latest 6 a.m. You know, to avoid to be in traffic jam. So I mean, we use those kind of the logic. Even we apply the governors, but unfortunately, governors say you are right, but the local authorities cannot be so understanding our concerns.
Yep. Okay. That's
another one point which I just skipped because it's not related with the this seminar, but we have some concerns about having road permits in Europe. We are member of the ESTA service in Europe, so ESTA association in Europe. We also ask their supporters to get the special road permit for heavy transportation in Europe for Turkish heavy transporters instead of using quota from the standard truck permission. Because the standard truck permission used by the thousands of the trucks. But in any case, we need to obtain special road permits if we pass through Austria, Slovenia, Germany, Holland, France, or any other European countries. So we are getting the special permit from all countries passing through according to the route. But on top of it, requesting from us to get the truck permit from the quota, which also decreasing quota for standard trucks. So Turkey already get the special condition with Austria, but we kindly ask to expand this condition more countries in Europe on top of the Austria.
Okay, yeah, it's good to be aware of this kind of issues, yeah, especially for the bridge engineers as well. So thank you very much, Selcuk, for your presentation. I think that was the end of the session. Thanks a lot. Yeah,
Thank you
can stop sharing your presentation, maybe. And I will turn Alp on, because we have another 5 minutes spared, because the last presenter was very quick, which is good. Yes, Alp.
Yes, thanks, Hulya, for...
My pleasure, always.
Excellent moderating the sessions. And I think we will have a 50-minute break. And during the break, we are going to show the sponsor videos and the Istanbul videos. So I hope you will. We'll start the next session at 12:45, and it will be about this structural design. There are intelligence inside that session. And if you have any question regarding sessions or anything, just let us know, or you can email us or write through the chat system. And I think from we'll make some adjustments, hopefully. Yes.
Yep. Okay. See you all. Bye.
Yes.
What time do we reassemble?
12:45.
12:45.
50 minutes.
Okay.
Yes.
Bridgewiz has been established in New York and expanded to the capital of Turkey, Ankara. As Bridgewiz, we provide reliable and affordable engineering services. Our workforce has more than 70% women in the team. Consulting and optimization, detailed evaluation of joints and bearings, condition assessment, and bridge engineering IT support are the provided services of the company. Bridgewiz Engineering is also a research and development company in the Technopolis of one of the top universities in Turkey, which researching joint artificial intelligence-based bridge management systems. At the same time, Bridgewiz supplies functional and engineering tools through tutorials and smart Bridgewiz calculators. As Bridgewiz, we can provide custom tools for your company in the forms of mobile or personal computer application.
TİS, Türkiye'nin ilk ve tek yerli ve milli deprem izolatörü. Dünyada kullanılan en son teknoloji, en yeni deprem yalıtımı sistemi. Hastaneler, veri merkezleri, konutlar, köprüler, okullar, iş ve alışveriş merkezleri, hatta tarihi yapılar, üst yapıyla temel arasına yerleştirilatörleriyle şimdi daha güvenli, şimdi daha sağlam. TİS, teknolojik izolatör sistemleri. Yapılara güç katar, hayatlara güven verir.
Reinforced concrete is one of the most economical and durable construction materials on the planet. When properly designed and maintained, concrete structures can last. There are times when it makes sense to demolish and rebuild structures, but all too often, the service life of a structure is unnecessarily cut short due to the widespread effects of corrosion and deterioration. In the construction industry, extending the service life and preserving concrete structures is the most economical and sustainable act too. Proper maintenance and periodic cleaning are simple and cost-effective activities that defer the requirement for major concrete restoration. Preserving or reusing existing infrastructure is one of the most sustainable activities that facility management can implement by mitigating pollution, reducing solid waste, and conserving natural resources. The Concrete Preservation Alliance consists of Vector Construction, Vector Corrosion Technologies, Vector Corrosion Services, and NDT Corporation. These four businesses have come together to create an informational website to promote sustainable practices in the construction industry. We hope the website will become a leading resource of information for owners and engineers who are interested in concrete preservation practices. We invite you to explore the pages of WeSafeStructures.info, where you will learn about the benefits of concrete and corrosion evaluations, concrete repair techniques, and extending the life of corroding structures, using coatings, overlays, cathodic protection, and other techniques. Please contact the Concrete Preservation Alliance or visit WeSafeStructures.info for more information.
to Istanbul Bridge Conference. You are invited to the Istanbul Bridge Conference. You are invited to the Istanbul Bridge Conference.
Hello, my name is Melike.
And I'm Dilara.
We are volunteer engineer for Istanbul Bridge Conference.
This year conference is going to be online, but in 2022 we hope to see you in Istanbul. Now let's discover the Sheraton.
The special Turkish delight here, made of honey, we have grapeseed flavor, fig flavor, Nutella, caramel pistachio, Oreo, caramel strawberry, honey pistachio, kiwi. Then also we have Nutella with nougat with angel hair. It's so good. Pistachio, and pomegranate, and also I close this pomegranate.
Konferansına siz değerli insanlar davetlisiniz. Merhaba arkadaşlar, İstanbul Köprü Konferansı'na hepiniz davetlisiniz. İstanbul Köprü Konferansı'na davetlisiniz.
Good night.
You are invited to Istanbul Bridge Conference 2022.
You are invited to Istanbul Bridge Conference.
You are invited to Istanbul Bridge Conference.
Hello, greetings from Sheraton Istanbul Hotel Ataköy. You are invited to Bridge Conference in Istanbul.
İstanbul Köprü Konferansı'na davetlisiniz. Merhaba arkadaşlar, İstanbul Köprü Konferansı'na hepiniz davetlisiniz. İstanbul Köprü Konferansı'na davetlisiniz.
You are invited to Istanbul Bridge Conference.
BridgeWiz has been established in New York and expanded to the capital of Turkey, Ankara. As BridgeWiz, we provide reliable and affordable engineering services. Our workforce has more than 70% women in the team. Consulting and optimization, detailed evaluation of joints and bearings, condition assessment and health monitoring, and bridge engineering IT support are the provided services of the company. BridgeWiz Engineering is also a research and development company in the Technopolis of one of the top universities in Turkey, which researching joints, bearings, and artificial intelligence-based bridge management systems. At the same time, BridgeWiz supplies educational and engineering tools through tutorials and smart BridgeWiz calculators. As BridgeWiz, we can provide custom tools for your company in the forms of mobile or personal computer application.
TİS, Türkiye'nin ilk ve tek yerli ve milli deprem izolatörü. Dünyada kullanılan en son teknoloji, en yeni deprem yalıtımı sistemi. Hastaneler, veri merkezleri, konutlar, köprüler, okullar, iş ve alışveriş merkezleri, hatta tarihi yapılar, üst yapıyla temel arasına yerleştirilen TİS deprem izolatörleriyle şimdi daha güvenli, şimdi daha sağlam. TİS teknolojik izolatör sistemleri. Yapılara güç katar, hayatlara güven verir.
Reinforced concrete is one of the most economical and durable construction materials on the planet. When properly designed and maintained, concrete structures can last hundreds of years. There are times when it makes sense to demolish and rebuild structures, but all too often, the service life of a structure is unnecessarily cut short due to the widespread effects of corrosion and deterioration. In the construction industry, extending the service life and preserving concrete structures is the most economical and sustainable activity that we can pursue. Proper maintenance and periodic cleaning are simple and cost-effective activities that defer the requirement for major concrete restoration. Preserving or reusing existing infrastructure is one of the most sustainable activities that facility management can implement by mitigating pollution, reducing solid waste, and conserving natural resources. The Concrete Preservation Alliance consists of vector construction, vector corrosion technology,